Video is about springs. And so here I have a spring that is unstretched. In other words, we're not pulling on the spring this way. It is uncompressed, so we're not pushing on it. But if we do, if we push on the spring down here, compress it, or we pull it, Hooke's law tells us that there is a force exerted by the spring, and I'll come to this over here in just a moment. The force exerted by the spring is equal to the spring constant, which is a lowercase k. Remember now we have kinetic energy, which is capital K, and spring constant will be lowercase k, so make sure you are writing that as lowercase. Now the force exerted by the spring is in newtons. The spring constant has a units of newtons per meter. That means for every meter that you compress it, that's how many newtons of force the spring is exerting. And x is how far the spring is compressed or stretched. In other words, the displacement from the equilibrium. That would be in meters. So if we take this spring that is uncompressed, unstretched, and we compress it, let's say, by a distance x, okay, that's the x that would go in this equation here, and the spring constant is a constant for any particular spring. It has its own spring constant, and they vary. That number varies. Now, if I were to pull on this spring and stretch it a distance x, and by the way, of course, this is the equilibrium position, but if we displace it this way and we're stretching it, we're pulling this way in the positive direction, but the force exerted by the spring would be in this direction against it. And so oftentimes you'll see this equation written as Fs equals negative k times x, where the negative is just showing the direction of the force. If you compress it, in other words, going in this direction, then the spring wants to push in the opposite direction. And again, this is just showing that the force exerted by the spring is moving opposite of that direction. So that's Hooke's law. And down here, which is more relevant to what our examples for today, is whenever you compress a spring, or stretch it for that matter, you are putting spring potential, you're storing spring potential energy, which is capital US, which is kx squared over 2. And so I had this written here from earlier. Of course, U means potential, and the subscript S is for the spring. Okay. Which of course is in units of joules. So let's go to some example here. We have two pictures, but it's the same spring, the same object. In position 1, we press an object, mass m, against a spring with spring constant k, and we move it from its equilibrium position. We compress it a distance x, which is 0.6 meters. There is no friction on this floor here, and so we can use the conservation of mechanical energy to figure out what is the speed of the block in position 2. Once we release the block and the spring decompresses, it's going to transfer some energy into that block there, and we can figure out what the speed is. The spring constant of the spring is 360 newtons per meter. The mass of the block is 4 kilograms. And so we can start by saying the mechanical energy at position 1 is equal to the mechanical energy at position 2. And because we have a spring here, we should write K1 plus UG1, and finally US1, the spring potential energy at position 1, is equal to K2 plus UG2 plus US2. Now, a couple of things. In position 1, the block is not moving. There is no speed to the block. And so again, if there's no speed, there is no kinetic energy. They don't give us a height at position 1, nor do they give us a height at position 2, but we do know that it's the same height. And because there is no height difference, we can really just say that the height here is 0. And since the height has not changed, this is also 0. And so there's no gravitational potential energy to note here. Now, there is spring potential energy in position 1, but in position 2, there is no spring potential energy. That spring is not compressed. And so, quite simply, the spring potential energy will be converted or transformed, is a better word, into the kinetic energy of a block later on. And so if you remember your conservation of energy, the law of conservation of energy, energy cannot be created nor destroyed, but it can be transformed. And that's what's happening here. So this is kx squared over 2 equals mv squared over 2. You can cancel 2. You can't cancel m because there is no m in this term over here. And we're trying to figure out the speed. So let's say kx squared over m is equal to v squared. And finally, we'll just square root. And before we have an answer, we need to plug in the numbers. This is 360.6 squared over the mass, which is 4. So I'll grab our calculator. Say 5.7 meters per second. Looks good to me there. Yeah, I was going to add anything I forgot to mention, but I think that was pretty much it. As you're going through your notes, always go back and see, do you remember why we made these 0? You know, it's important to know when we can make those things 0. Okay. Next example. Here's a spring in its equilibrium position. So this is where the spring is normally. In position 1, we are placing a ball against it. It is compressed. The distance or the displacement is 0.2 meters. The mass of the ball is 0.5 kilograms. And the spring constant of this spring is 120 newtons per meter. In position 2, we've released the ball and the spring is back in the equilibrium position and the ball has moved up to its maximum height. And so our question is, what is that maximum height? How far is that? So we'll use the conservation of mechanical energy. We can say K1 plus UG1 plus US1 equals K2 plus UG2 plus US2. And so right away there are some energies that are 0. And let's take a look at position 1. Okay, the ball is here and is pressed against the spring. There is spring potential energy because the spring is compressed and it's storing energy. The height at position 1 for the ball is 0, so there is 0 gravitational potential energy. And the ball is not moving at position 1, and so K is 0. At position 2, the spring no longer is compressed. There is no spring potential energy being stored. There is gravitational potential energy, UG2, and the kinetic energy of the ball at position 2, well, if you remember back from kinematics, when a object like this is essentially in free fall and it's reached its maximum height at the speed. In those days, we said velocity is zero. And so there is no kinetic energy at this position here. Uh, in between here somewhere it did, but it's slowing down and it'll reach zero kinetic energy there. And so all of the spring potential energy has been transformed into gravitational potential energy. We will say kx squared over 2 is equal to mgh. And we're trying to solve for h. So we can rewrite this as kx squared over 2 mg equals h. Of course, we can't cancel m. And so we'll say 120 times 0.2 squared over 2 times 0.5 times 10 is equal to the height, which is a height of 0.48 meters. Cool. Yeah, I might as well add, those are all the examples for this about springs. Might as well add this little piece here about a system. Well, what we're talking about here is, let's write this down. An object, let's say it's a ball, and let's say it can be moving. An object can have kinetic energy. It has a mass, it has a speed, so we can calculate its kinetic energy. But something we're noting here is because like on the AP exam, they like to distinguish between, oh, not distinguish, but they would like to sometimes ask you about the energy of the ball or energy of the object, let's say. And so my point is that the object can have kinetic energy, but an object alone cannot have gravitational potential energy. Um, and so they wouldn't say they like to trick you, but they might ask it in such a way where they ask about the energy of an object, where we can only say that kinetic energy is the energy of the object. And the reason why you can't say that gravitational potential energy, that an object has gravitational potential energy is, sorry, not the M, it's because of G. G is the gravitational field, which we can think of as being part of the Earth. It's created by the Earth's mass. And so only a system, and here we go, here only a system can have gravitational potential energy because the object will have mass m, but the gravitational field is part of that Earth system. And so right here we wrote an object by itself cannot have gravitational potential energy. Gravitational potential energy can only exist in a system that includes the object and the Earth, or objects and the Earth. And so sometime we might have a question where making that little distinction matters. And on the AP exam, if they do ask a question about that, yeah, it does matter. Um, we have to think about that consideration. Anyway, besides that, that's it for today's video.